Hi everybody, welcome back to this series of short demonstrations of the capabilities of Cerberus 2080, the multiprocessor 8-bit microcomputer. In episode 1 we covered the basics of the functionality, the basics of the architecture. Then in episode 2 we covered the flexibility, how you can create virtual kernel and basic ROMs anywhere in the 64 kilobytes of address space, which is entirely RAM, the ROM being embedded into the I/O controller. And then in episode 3, the last episode, we looked at the graphics capabilities of Cerberus, programmable tile graphics that uses the 256 character definitions in this RAM here, as if they were pseudo tiles, pseudo sprites, so to say, and we played around with a port of Manic Miner for Cerberus 2080. So in this episode, we are going to do two things. We are going to show Dean Belfield's port of BBC Basic, the basic interpreter created by Acorn Computers in the 80s, the best basic interpreter of the 80s. This time it has been ported to Cerberus's Z80. In episode 2, we saw BBC Basic running on the 6502. Now we will see it running on the Z80. And then we will run some benchmark applications written in BBC Basic running on the Z80 in here. And we will then, towards the end of this episode, do a brief comparison with other machines from back in the day and a machine of today, namely the ZX Spectrum Next. And I will comment a little bit around that. So as you see now on the screen that we have on, the current BIOS loaded in the I/O controller is AndyTunes XFE version 1.0 BIOS. That's the one we had loaded in the previous episode. It's still there because it's stored in Flash. It's non-volatile. Once you upload the BIOS, if you don't want a different BIOS, the BIOS you uploaded will be there forever. But now we need to upload Dean Belfield's BIOS. As I explained before, it's very difficult to stop smart programmers from setting up the system the way they want, the way they think is best. So fitting into this pattern, Dean made the modifications he needed in order to get BBC Basic running on the Z80. And again, in this case, it was really needed because the original BIOS does not allow for the CPUs to tell the I/O controller to save or load files. The CPU is the master. So Dean modified it so the Z80 can tell the I/O controller to save and load files into the microSD card here at the back of the architecture of the board. So let's upload Dean's BIOS now. Again, it's just one command on my PC's command prompt window. So it's uploading now. You see the little blinking LEDs there. Once it's done uploading, it will verify what it has uploaded. The upload now is complete, so now it's verifying it. And then the computer will automatically reset itself. There we go. We have Dean's BIOS loaded up now here on the I/O controller. We can actually even remove this. As you see, he changed the defaults. Now the BIOS is by default set to the Z80, which is not surprising. He was porting a basic interpreter to the Z80. And at 8 megahertz, which is also not surprising. The reason for the slow mode at 4 megahertz is just some games that don't use a regular interrupt to set the timing, which may then become too fast to be played at 8 megahertz. But for a basic interpreter, you just want maximum performance, so I understand that. Now, like for Gordon's interpreter, we need now to load the actual interpreter somewhere in the 60 kilobytes of memory across these two system SRAMs in here. I just have to remember what the name of the file is here in the microSD card, which has the interpreter. Basic 4 is Gordon's. Oh, where the hell is it? Am I becoming blind? Oh, it's right there, bbcbasic.bin. I'm becoming blind, bbcbasic.bin. I don't need to specify an address. Dean set it up to load on the first address available according to the standard memory map of Cerberus on the low memory, and that's address 202, which is the default of the load command. So if you go to list 202, there it is. That's where the basic interpreter is. So we can just run it. There we are. We are now in the basic prompt of BBC Basic, Acorn BBC Basic running on the Z80. And we can do the usual stuff. And of course, we are going to do the obligatory hello world. We cannot miss that. Hello world, semicolon, 20, go to 10, and run. Hello world from the Z80 in Cerberus, running BBC Basic. Isn't that cool? I find it pretty cool because of all the nostalgia thing, clear screen. There is a game here. It's a text-based game. I'm curious about it. It's called Animal.bbc. It's in Basic, I think. Yeah, that file was there. I saw it. Let's look at it. 146 lines of Basic. It's some kind of text. Yeah, it's definitely some kind of text game. So let's just run it. See what it does. Animal, creative computing, Morristown, New Jersey, from the other side of the pond. Play Guess the Animal. Are you thinking of an animal? Yeah, I'm thinking of my cat. Does it fly? No. Cats don't fly. Is it a goldfish? No, it's not a goldfish. Okay, I give up. So much for an AI. Tell me what animal you were thinking. Oh, it wants to learn from you. That's how it... Oh, I see. Please tell me a question that would distinguish a cat from a goldfish. Does it walk? A cat walks, a goldfish doesn't. For a cat, the answer would be yes. Are you thinking of an animal? Yes. Does it fly? No, cats don't fly. Does it walk? Yes, cats walk. Is it a cat? Oh, congratulations, you're amazingly smart. Try another one? No, thank you very much. Do you want to save this on disk? No, thank you very much. So much for a game. Okay, let's load the benchmarks now. That's what we set out to do today. So benchmark1.bbc. This stuff has been run in other computers. So we're going to use the exact same code that has been run on other computers. Let's look at this. It's just an empty for loop from 1 to 1000. And it takes the time in the beginning, prints an S for start, I suppose. And then once it's done just going through an empty for loop, it prints an E for end, and then prints the elapsed time. Sounds reasonable enough. Let's run. It's just an empty for loop. It will be done in a blink. Yeah, 0.42 seconds. Fair enough. Let's load the next one. Benchmark 2.bbc. Let's have a look. Hopefully it's a little more complex. Yeah, it defines some variables. And instead of a for loop, we have a pseudo for loop. It's just an if statement that plays the role. Yeah, this will be less efficient, of course, for the basic interpreter to interpret, because this is essentially a for loop written in a different way. So it probably would take longer. 1.82. Fair enough. Next one. Benchmark 3.bbc. Let's have a look at it. Oh, there are some mathematical operations now for variable a. If the interpreter is clever enough, of course, it will eliminate the plus k and the minus k because they cancel each other out. Let's see how it goes. Yeah, this will take longer because even eliminating those, you still have the k divided by k times k, so it's 1 over k. You still have that 5.8. 5.8. I wonder if it's different if you run at different times. Shouldn't be. Yeah, 5.8. Load benchmark. We are now in the fourth one. .bbc. Let me just clear the screen once and list it. Oh yeah, now the operations numbers are used, integer numbers instead of variables. So probably this will throw the interpreter off in trying to optimize things. So this should take a fraction more than the previous one. A small amount of time more than the previous one. Previous was 5.78. This should be, I don't know, 6.4. 6.4 seconds. Now, we have eight benchmarks, so we are going now for benchmark 5.bbc. Let's have a look at it. Oh, there is a call to a subroutine now. Line 520 is go sub 820, which is just a return. It's an empty subroutine, but the interpreter will still have to switch context. It will still have to save the program counter in the stack and switch context and then pop it from the stack to recover. So yeah, this would take a little bit longer. It shouldn't take much longer because it's an empty subroutine. So it's a push and a pop from the stack and one context switch. So this will be a fraction of a second longer if things are consistent and predictable, which they should be. Yeah, 6.86 instead of 6.4. That sounds reasonable enough. So benchmark, that's number 6 now. Benchmark 6.bbc. Oops. Hi. Tiny keyboard. Now this one has a for loop within a pseudo loop implemented with an if statement. Yeah, this one would, this one would clearly take a couple of seconds more because of that built-in for loop. Even though the for loop is empty, the interpreter still has to count 1 to 5. 9.86 instead of 6.86, so that's exactly 3 seconds longer. So now we are in benchmark 7. There are 8, so this is one before, of course, that will not work. Benchmark 7.bbc, this is the one before last. Yeah, this has a little array, a one-dimensional array that has to be dimensioned, M5, and then a value attribution is done within the small for loop, within the pseudo for loop done with an if statement. This will again take a couple of seconds more than the previous. The previous one was at 9.86. I guess, yeah, this one will go to 15. That would be my guess. 16 maybe. 15, 16. That would be my guess. 14.16. That's not bad. That's not bad at all. 14.16. And now we are at the last benchmark. That's benchmark 8.bbc for BBC Basic. Let's list this thing. Ooh, this has some trigonometry. This has a log, a sine. And of course, these complex mathematical functions, they are implemented via numerical algorithms, which is basically a guessing game. It's guess and test and improve your guess, test again, improve your guess. And this stuff takes quite some time because it has to converge. Let's run it. But this I would guess this one will edge close to 20 seconds. Unless this is a pretty clever basic interpreter. even at 8 megahertz, I think this will edge on 20 seconds, maybe even a tiny little bit more. Oh, 16.86. Okay, now that's not bad. So let's now go and have a look how these results stack up to a couple of other computers, so we see where we stand with Cerberus. So here are the final tabulated results. I highlighted this column here because these are Cerberus's results running at 8 megahertz. And all the results you see here, all the numbers are in seconds. That's the benchmark number running from 1 to 8, as you saw me measure. And then we compare it with 3 other machines, the Spectrum Next running at 3.5 megahertz, the same Spectrum Next running at, oops, sorry, I went too far, running at 28 megahertz, then the classical ZX Spectrum running at 3.5 megahertz. These 3 machines here are Z80 machines. And then we also compare to the BBC Micro, which was a 6502 machine running at 2 megahertz. But it's relevant to compare because that's the machine that the interpreter was initially written for. The BBC Basic Interpreter was written for the BBC Micro. Now here you see the numbers. Of course, these are fractions of seconds, so the lower the better. But it becomes difficult here because these things are running at different clock speeds. It becomes difficult to compare the architectures to one another. You might say, well, the ability to run at higher clock speeds is relevant because it tells you something about the quality of the PCB, the quality of the design, because it's difficult to be able to run a computer robustly, reliably at higher clock speeds. Okay, there is an argument for that. But in this case, it's a difficult argument because, for instance, the Spectrum Next doesn't care about using through-hole 5 volts technology to stay retro. It just uses modern SMD 3.3 or whatever, 2.8, 2.5 volts. So the board design is also different, and those parts inherently run at higher clock speeds. So it's a difficult comparison. But let's just have a very quick look. Cerberus is faster than the Spectrum running at 3.5 megahertz. No surprise there. It is faster than the BBC Micro. But again, the BBC Micro runs at 2 megahertz. So the best way to compare this is to normalize for the clock speed. So we take the clock speed out of the equation and we just compare the quality of the design. And then we are not also comparing anymore the quality of the PCB because there, the achievable clock speed is a relevant benchmark. But let's only compare the design without the PCB. So we will normalize the clock speed away. And to do that, we take each of these numbers, multiply by the respective clock speed, and then divide by the highest clock speed, which is 28. So in the case of this column here, nothing changes because we are multiplying by 28 and dividing by 28. But in the case of Cerberus and the others, in the case of Cerberus, we multiply by 8 and divide by 28. In this case here, we multiply by 3.5 and divide by 28, and so on and so forth. And then what we get is this. And you cannot interpret these results as seconds anymore because this is all normalized. But again, the lower the better. So you see here that after clock speed is normalized away, Cerberus is still faster than the Next and both versions of the Next. Consistently, for each of these lines, Cerberus's numbers are lower than the Spectrum Next numbers in both rows. Cerberus is also better than the ZX Spectrum consistently for the entire column, but nobody beats the BBC Micro. It has the lowest numbers. Now, that's tricky because what we are comparing now is the quality of the basic interpreter, because the original basic interpreter was written in 6502 assembly for the BBC Micro. and it was then translated into Z8 assembly. So the quality of that translation comes into play now. We are no longer comparing apples to apples. So this is a difficult difficult comparison to make, but I will leave it in for reference. So now if we plot this in a graph, you see here Cerberus in orange. So Cerberus is here, Cerberus is here, Cerberus is here. And then for each benchmark number from 1 to 8, we plot a little bar corresponding to the normalized result. And the lower the bar, the faster the computer. And what you see again is that Cerberus is consistently faster than everybody. So this is lower than this, and this, except then the BBC Micro. But then again, it's a difficult comparison to make because the quality of the translation is built into this result. And of course, Cerberus has nothing to do with that. That was a programming job someone did years ago. So given this, I mean, Cerberus is not much faster than the next. It can be significantly faster than the original Spectrum, which scores very badly for benchmark 6 all the way to 8. The original Spectrum is terrible. But again, it was an architecture optimized for cost. So the real interesting comparison is amongst the 3 first columns, orange, gray, and yellow. That's the comparison that is apples to some extent, because Cerberus makes the sacrifice of not using SMD and low volt technology. It tries to be retro. But these are all 21st century computers running the same basic interpreter already translated to Z80 code. So whether it's good or bad, it doesn't matter. It's an equal variable for all 3. So these are the nice comparisons to make. And Cerberus does pretty well. It's not massively better than the Spectrum Next. The fact that it's better at all already surprised me, since I designed Cerberus to be an educative platform, to be didactical, and to be retro. But it is always better for all of the 8 benchmarks. But this is pretty good. I'm pretty happy. And this brings this little series to an end. I hope you've enjoyed it. If you're interested, you can always download all the files of Cerberus from my GitHub repository. You can build it yourself. It's all through-hole technology, fairly easy to solder for experienced hobbyists. If you're a beginner in electronics, don't start with Cerberus. Do yourself a favor and start with something simpler. But if you have some experience, you can do it. You can buy the components yourself, order the board yourself, and build your own Cerberus. Or if you prefer, you can order from the Dutch Home Computer Museum. They sell kits with all the parts you need already pre-programmed. In the case of the 3 CPLDs and the I/O controller, they are all already pre-programmed. And you can even buy an assembled unit from them already put together without the case, but the main board and all the components that you need to use Cerberus. If you do that, I hope you enjoy. I hope you consider it a good investment in your own education and fun. And I will see you next time for the next project. And the next project is something that may surprise a lot of you, but I will discuss it later. In the meantime, take care, stay safe, and I'll see you around.